Hi, welcome to this video series on Diffie-Hellman parameter setup. We have been talking about the properties of the group, generator, and subgroup, and so on. In this segment, I actually wanted to take a look at RFC 7919, which is a publicly available document, as you can see from the tools.ietf.org site. I was discussing this with a friend of mine, and he asked me an interesting question. Here is the group P, and here is the generator G, and then the subgroup Q. What happens if I change the group generator, say from G equal to 2 to some other number? What type of security implications that will have? That's a very interesting question, actually. I thought I will spend some time clarifying it. So before we dive into the details of it, I would like to recall some important properties of the cyclic group, and particularly the quadratic residue concept that I talked earlier. So let me run this little Python helper code that will help us to understand this very quickly. So I have here a cyclic group of order, in fact, a cyclic group of order 10, like the ZP star 11, right? P is 11. What it means is that you see the first row is generated by G equal to 1. Of course, when G is 1, nothing is generated other than 1. 2 generates the entire cyclic group, 1, 2, 3, 4. All of the elements are there. You can check for yourself. There are 10 elements. Those are the 10 elements of the group, multiplicative group Z star 11. On the other hand, 3 actually only generates 5 elements, 4 5 elements, 5 also 5 elements. 6, 7, and 8 generate the complete group, of course. 9 generates group of order 5. After that, it will repeat. All of these things are basically repeat of the first 5 elements will repeat again, and so on. Okay, so they will repeat. What you're seeing is also that during if you look at the second column, for example, we have numbers like 4, 9, 5, 3, 5, 9, 4, 1. So basically 1, 3, 5, 4, 5, 9, right? And there is an interesting property there. If you take, say, for example, number 4, and look at the row 4, it exactly has the same set of elements. Basically, 4 generates the same set of elements as the elements of the second column. Okay. If you take the number 5, 5 also generates exactly the same set of elements, same as the column number 2's, right? Column number 2 has 1, 3, 5. You can check yourself. Okay. What about number 9? 9 also generates exactly the same as column number 2. Okay, of course. It's interesting to see that these numbers like 3, 9, 5, 4. Okay, I was talking about the second column, right? 4, 9, 5, and 3. They all generate exactly the same elements as we see as part of the second column. That's an interesting property of quadratic residue. Okay. If an element is a quadratic residue, remember what it means is that it can be written as power of 2. For example, number 5 is a quadratic residue because we can write 5 as 4 square. How do we write 5? 5 is equal to 4 square in mod 11. We can check 4 square is 16, 16 mod 11 is 5. Okay, so 5 is a quadratic residue because it can be written as a power of 2. So quadratic residue. Okay, quadratic residue. Sorry, it's a mouthful word. Okay, there's a QR is the notation. All right, so we do see that the quadratic residues actually form a group because, as I mentioned, if you take the second column, you would see exactly the same members if you go through row wise. For example, if you take the number 4, 4 generates 4, 5, 9, 3, 1, which is, of course, we know it's a subgroup. Okay, every row is a subgroup, and we can see that quadratic residue generates is a subgroup. Actually, is a subgroup. All right. These are the important observations we need for the question that I already wanted to answer, is that what happens if I change the G? That's what my original topic is. Okay, so this is quick recall of the basics. Let's clear this, and now let's get into the main topic that I would like to discuss is that what happens if my G is not 2, something else. Okay, first of all, what is the purpose of having G equal to 2? We can quickly do some simple exercise. Actually, I have named it somewhat not good, but that's okay. We have P, Q, and G. It's exactly the same as what you see from the RFC, right? And I'm going to just copy this, put it into Python, and show you something important. Okay. So what is the document saying? The document is saying G equal to 2 generates a subgroup of order Q. How do we check that? Let's assume P and Q are primes. We have not checked it. We can believe the document is correct. Okay. P and Q are primes. So in that case, what shall we do? We can do a very simple check. Let me show you what. Print pow G power Q mod P. What I'm doing is I'm computing G power Q mod P, right? Why do I do that? If I do that, right, one moment. If G power Q mod P, if this is equal to 1 mod P, what can we say? We can be sure that G generates a subgroup of order Q. That's basically what we wanted to confirm. So can we do that now? I'm going to do this. Yeah. Of course, G equal to 2 is a subgroup of order Q, because we can see that it confirms the theory. Okay. What about G equal to 3? If we do that, 3 is also a generator of a subgroup. We can use 3 as well. What about 4? We can try that. Yes, we can use 4. What about 5? 5 is also a subgroup. So 5 also generates the same subgroup. What about 6? Same subgroup. What about 7? Aha, 7 is not generating the subgroup of order Q. Okay, now comes the question. So what does it? What kind of group does 7 generate then? Well, we are in a special context, right? We are in the context of safe primes, right? We argued that this is a safe prime. We didn't check that, but we can quickly check it if you wanted to make sure. We can just say print, right? Okay, let me do this. Let's do 2 times Q plus 1. Let's call it RHS, the right hand side, right? 2 times Q plus 1. And let's see if P is equal to, well, I could have used directly that. Okay, anyway, just print equal, right? Print safe prime. Yeah, it's safe prime. We confirmed it. So the data they have given on the RFC is a safe prime, just to be clear. So now the question is, what kind of group does G equal to 7 generate? We know for sure G equal to 7 doesn't generate a subgroup of order Q. So what are the possible subgroups we have? We are working with a safe prime, right? In the context of a safe prime, the subgroups, what are the orders of the subgroup? It can be 1, 2, Q, or 2Q because of Lagrange's theorem I talked about earlier. Okay, so these are the only 4 possible subgroup orders we can have. So that means, of course, G equal to 7 doesn't generate a subgroup of order 1. If it was, it would be just generating only 1, right? Number 1. What we are seeing is not a number 1. We're seeing a very large number printed here on this page. So what about number 2? Number 2 means we have a special group, right? Like this. It must be the group 1 comma P minus 1, but we are not seeing that either. This number is not same as the big number that you're seeing on the screen is not the same as P minus 1. So already we checked that it is not generating the subgroup of order Q. Therefore, it must be generating the entire group. Okay, so it must be generating the group of order P, P minus 1 to be more precise. So it must be generating the original group. Okay, so G equal to 7 actually generates the entire group. Okay, what we are going to do now is, what type of information leakage will happen if I use G equal to 7 as opposed to G equal to 2 or 3 or 4 or 5, for example. So we can do some simple checks now. Okay, so I argue that G equal to 7 will leak the least significant bit of the secret numbers. Okay, the secrets of Alice and Bob, exponents. Okay, so what I mean, let me confirm and more clearly. What I'm trying to say is that if you remember the key exchange model. Okay, let me quickly show the formal model. Yeah, here it is. The formal model is that, one moment. So, sorry for the delay. The exponent, okay, here they are. Alice and Bob took some time to come up. The private exponents are X and Y, right, respectively, for Alice and Bob. If we choose the wrong G, in this case, for example, G is equal to 7, I will show you, we can find out the least significant bit of X or Y, okay? In fact, both. So it's enough to show you only one, right? So we will do this. Let us assume that Alice picked X is equal to 3. Of course, X is equal to 3 is such a small number, you will brute force it when you and break the Diffie-Hellman. But 3 we know for sure is an odd number. So I will show you that that the attacker Eve can tell that the least significant bit is easy to predict. Okay, I will show you how. Okay, so what we have to do is that we need to, of course, compute the public key of Alice, which is nothing but G power X in mod P, right? Okay, now we will apply this interesting theorem from Euler. Euler discovered this beautiful theorem that we will leverage. An element is an element. It's something called quadratic residue he discovered, right? How do you know whether an element generates? An element can be written as power of 2. So he said like this: an element A can be written as power of 2 if and only if A power P minus 1 by 2, the whole P minus 1 by 2 is an exponent, is equal to 1 mod P. Okay, if this is true, A is a quadratic residue. A must be a quadratic residue. So that means A must be able, we can write A as power of 2. That's what he's trying to say. Okay, so let's consider this now. In this context, we should compute A power P minus 1 by 2, right? So we will do this. We will print A. Well, we need to print A comma P minus 1 by 2 comma P. Okay, what shall we do? Okay, we see some really large number. A power P minus 1 by 2 mod P is not 1. Therefore, we can conclude this number capital A is not a square number. Okay. Okay, what it means is that the number A cannot be written as power of 2. Okay, which means the exponent must have been an odd number. If it was an even number, of course, you could have written as power of 2 is 2 times something, right? So we can conclude that yeah, the power of the secret exponent Alice chosen must be an odd number. Remember, if it was an even number, we could very well write it as power of 2, right? Okay, let me now convince you that that's the case for even number. Maybe that's better. Okay, so I'll do the same with X being, say, 6, which is an even number. So let me compute the public key of Alice again. And now let's compute the Euler's criterion, which is 1. Okay, this tells us that the power of x, the value of x must be an even number. Otherwise, we wouldn't have gotten 1. This is an if and only if condition. We will, according to Euler's theorem, we will get if a power p minus 1 by 2 is congruent to 1 mod p, then we can be sure that a is a quadratic residue, meaning a must be it must be possible to express a as power of 2. Okay, that's basically what we are trying to say. What we have seen is that if G is generating the complete group as opposed to the subgroup of order Q, we can find out whether the least significant bit is 1 or 0. That's what we have convinced so far. Okay, which means going back to the RFC, which is not correct RFC. One moment. Going back to the RFC, we can see that the reason they have chosen G equal to 2 is that it generates the one of the reasons. The other reasons as well, it generates the subgroup of order Q, and we have seen that choosing G equal to 2 actually hides the least significant bit. I will confirm that quickly. So let me reset my G to be 2, right? And let's compute the case where what is my current x? Current x is 6. We can see current x is 6. So let's confirm that this we can hide this fact that x is even or odd. Okay, how do we do that? We have to compute the public key, and we print the Euler's criterion, which comes out to be 1. Okay, what about the case when x is odd? Let's consider the case x is odd. We will do the same again, and we can check it's also 1. So it doesn't matter whether x is odd or even. If we choose G, which is basically a quadratic residue, then we can be sure that we hide the least significant bit. Okay, that's one of the interesting properties I would like to demonstrate to you. Okay, I hope that that's clear. What I am actually trying to say is that we can take the simple cyclic group, small number, and we can just look at the generator of this group. Okay, as I said, the entire group is generated by numbers like 2, 6, 7, 8, but we are interested in a subgroup of order 5, right? 11 is 2 times 5 plus 1, which is generated by number 4, 9, 5, 3. So we can take any of the numbers. If we take G is equal to 4, and it doesn't matter whether the exponent is even or odd, it's going to still generate a new number which will exactly sit in the column number 2. Okay, which means whatever value for the exponent we choose, we are going to see another quadratic number or a quadratic residue. Okay, so there's no way to distinguish between the odd case and the even case. That's the reason why we need to be careful when we just use something like this. We don't want to change and mess with these values unless we understand all of the things, all of the details. Okay, that's basically it. Thank you.